The idea was revolutionary from the start. It was a way to observe the Earth at a fraction of the cost.
The solution had always been to build big satellites, expensive satellites. We decided to do the opposite.
JPL took 2 measurement systems, previously the size of a school bus, shrunk each down to the size of a shoebox, and launched them into space. That was the job. Those 2 satellites then went on to redefine the possibilities for future Earth science missions.
So one problem that we always run into with Earth science missions is that we're not able to really observe how weather changes. Imagine a satellite flying over the Earth that observes a storm. It's observing that storm at one instant in time. It takes a whole nother orbit, about 90 minutes for it to come around and see that storm again. In the meantime, the storm may have moved, it may have changed, and we don't see how that happens. Our idea was that if we could launch multiple satellites separated by just a few minutes, we would get to watch the storm as it evolves and changes with time.
But it couldn't be just any kind of satellite. It had to be a CubeSat. CubeSats are small and inexpensive, so you can launch 100 for the cost of one big satellite. And even when you launch them, you need to make sure that they can measure rain from space, which is something that CubeSats have never done before. So that's how RainCube and Tempest were born.
CubeSat missions are risky from the start. We always said that we would have been happy if the missions failed, as long as we could figure out why they failed. The results we got exceeded all expectations.
And Antares lifting off the first
After
stage.
5 years of development, RainCube and Tempest were both selected to launch the International Space Station. From there, it was just a waiting game until they were deployed to space.
The deployment to space is the first time the spacecraft is put to the test, and CubeSats are so small that every single part needs to work. If any one part fails, it can be mission over.
3, 2, 1, deploy.
After RainCube, it was Tempest D's turn.
3, 2, 1, deploy.
Oh, that wasn't supposed to happen.
So the last thing that you want to hear when your satellite deploys is, oh no, that shouldn't have happened. But it turns out the satellite was designed for that scenario, and just 2 minutes later, the satellite turned and looked at the sun, and we knew it was going to be okay.
But the launch was only the beginning of the journey. 2 months later, a tropical storm in southeast Guam began to intensify and turned into what is now known as Typhoon Trami. Miles above the scene were our 2 young CubeSats.
It was serendipity at its best. RainCube and Tempest D were at exactly the right place at just the right time. But what made this extraordinary was how these 2 small satellites rose up to the occasion. When RainCube and Tempest D looked down at the typhoon from space, they saw 2 very different but complementary pictures. Tempest D is built to capture horizontal slices of the storm, so it was able to observe the breadth of the storm at different altitudes. RainCube, on the other hand, has the vertical perspective. It looks at only one point of the storm at a time, but can observe the storm from its top all the way down to the surface. As it orbits the Earth, this view from RainCube reveals a vertical cross-section of the storm. That's when the 2 teams had the idea to fuse both sets of data together. What emerged was a crystal clear, 3-dimensional picture of the eye of the typhoon.
This proves something that we had only been able to guess at before. CubeSats not only work, but they can work together.
And this is just the beginning. RainCube and Tempest D have been the pioneers for an entirely new and innovative way of making satellites to observe and study Earth. Because now we know with certainty that even the tiniest satellites can dare mighty things.